Welcome everybody to this session, which is the presentation of the Barnett lecture for 2019. And I know, although I was unable to be here myself, many of you will have been at the awards ceremony last night. So I know Marian will forgive me if I don't repeat the information that was given out there, except to say that it's not only self-evidently a highly appropriate award for Marian. It's a particular personal pleasure because I've known Marian for a very long time, and she was one of the people like myself and John Torn, another earlier Barnett Award winner, who worked quite closely with Vic Barnett in the early days of the Spruce initiative that he set up around about 1990. And although the environment was certainly a topic of interest in 1990, it didn't have the prominence it has today. And so it was really quite a far-sighted initiative of Vic Barnett to set up the Spruce initiative. Spruce was one of the more contrived acronyms I've encountered in my life, standing for Statistics for Public Resource Utilities and Care of the Environment. But now the environment is very, very mainstream, and so it's really very nice that the RSS has an award particularly dedicated to environmental statistics, and certainly all of those of us who consider the late Vic Barnett a colleague and friend are pleased that his name is associated with it. So, without further ado, Professor Marian Scott from the University of Glasgow has a long and very, very impressive record of research in the physical sciences associated with the environment, and that's reflected in the title of her Barnett lecture, which is probably visible all night already, so I won't repeat it except to hand over to Marian to deliver her lecture, and we can congratulate her once more on her award.
So thank you very much for those kind words, Peter. Thank you very much to the RSS for making this award. I'm very honoured. The title is slightly tongue-in-cheek. Data lakes, data deluges, digital environment, digital landscape are all terminology that seems to be creeping in and becoming more and more trying to be sold. And I just want to reflect a little bit in terms of what that actually means for what we're doing, what the mainstream kind of pushes are in terms of what the big environmental questions are, and where data and statistics and data science and so on fit into that story. Now, as I said yesterday as well, collaboration is absolutely key. None of this work has been done in isolation, and I've named a few of my colleagues in particular who've been instrumental in many of the applications that I'm going to talk about, and I've also mentioned some of the funding for some of the more recent work. As Peter said, it is very appropriate that we're acknowledging Vic. As Peter said, we knew him for a very long time, we worked with him, and he did have a great, if you like, vision of how important statistics was going to be in environmental sciences going forward. So absolutely, it's a great honour to be giving a lecture in his name. It's always difficult to know what you should present in a lecture like this. So I've tried to break it up a little bit into some narrative, some story, to encourage us all to get involved and become engaged in debates around the environment and changes in the environment in its broadest sense, to think about what some of the statistical challenges are and have been, and to think about what some of the challenges are and the vision that we might have for how we can contribute going forward. Now, as I said, data lakes, data deluges, and the digital environment or landscape are all slightly buzzy at the minute. If you look at potential funding currently, UKRI are talking about the digital environment. UKRI have a call out for making decisions at landscape scales within the environment, what the mathematical and statistical challenges are. And of course, we all follow the money. Maybe. But I hope that I can reflect here a little bit in terms of how, in a sense, it's not just money in terms of research funding that's driving this work. It's actually reflecting our own concerns about what is happening in the environment and how we need to be all engaged in this. So in terms of the data lakes, I think it's fair to say that technology is moving on. We're all carrying mobile phones, generating regular, frequent, high priority, high precision data streams. So lots of data coming online. Data deluges, Well, a deluge in some sense kind of implies that maybe there's a flood on the horizon. And there's always this question of, is there just too much? Do we really need all of it? Because it's fairly true to say that in many circumstances, we take this high-frequency data and we kind of aggregate it to make it simpler to work with. Digital environment or landscape is this kind of vision that we will have a fully quantified environment and its supporting ecosystems to help us make decisions, perhaps, about how we're going to manage going forward, what the resources are that we have, which are limited, but which actually support all of life on this particular planet. So more and more data streams coming on, interesting gaps in those data streams, and hopefully some interesting stories to tease out of them, because that really is what drives much of what we do. It's a curiosity about how things in the environment are related to each other, how they're changing, and how what we are doing are, in a sense, driving some of those changes. I have to put this one up. You know, artificial intelligence, the rise of the machines, another one of those buzzy areas that's very much the flavor of the month. This particular publication talks about 8 ways that artificial intelligence are going to help save the planet. One of them, I think, reflects the digital environment context in terms of it talks about, as a vision, that we want to have a digital geospatial dashboard for the planet that will enable monitoring, modeling, and management. So there we are. That's the context in terms of the vision of the digital environment. If you live in rural Scotland, this is a mockery at the minute. You know, satellite coverage, telephone coverage, network coverage, huge holes. So it definitely still is a vision going forward. But where there's a will, there will be a way. This is a PwC figure just talking about what some of the priority environmental challenges actually are. Climate change, all the way through to, if you like, air quality, water quality, resilience. So there's a huge array of particular challenges here, and you could argue that we as statisticians and data scientists can absolutely support how we move forward in this context to address some of these challenges. They're not trivial, I would have to say. I wanted to just kind of put this one up in terms of there has been a little bit, if you like, of friction around the language of, are you a data scientist? Are you a data analyst? Are you a statistician? But I think irrespective of those labels, you know, what has characterized much of what I have done and with my colleagues is actually really been curiosity driven to learn from data. And that to me, you know, if you take the word data scientist, if you turn around and say, well, you're studying the science of data, that's what we do. But we're needing to learn from the data that we have. We also need to think about how we should be better improving how we collect them and what implications that have, because that's how we're going to improve our understanding and our knowledge, and that's what we're using to help support some of the decisions that we're going to make. Now, I'm not completely naive. We've had some discussion about, you know, scientific evidence isn't the sole if you like, driver of decisions being made at high political levels. That's absolutely true, but we have to make sure that that dialogue is there and that science is sound and is explained in a way that will be part of the decision-making process. So I think we need statistical models to understand, to explain, and to predict. And in this digital environment, then we're going to have to be thinking about smart ways of producing computationally efficient modeling and visualization, which happens in real time and which is available to policymakers, regulators, civil servants, interested parties to make some of those decisions. That's the engagement process, so that we're all engaged in this. Now, as I've said, if I look back over all of the examples that I can think about, it has been curiosity driven. It's been trying to understand patterns, what's changing, what's driving the changes, how sure are we? And those are all required as part of that decision-making process. So that's really, as if you like, the kind of the narrative behind what I think would characterize many of the examples that I've been involved in. Now, this is a quote from 2001 by Jerome Friedman, and it just simply says that the nature of data is constantly evolving. It's constantly changing. And as statisticians, we need to evolve along with this. It makes the point about 20, 30, 40 years ago, most data was manually collected. Now we're moving on to it's basically no longer mainly manually collected. So we're evolving with that, and our statistical approaches are evolving with that. And I've got a couple of examples here. These are just recent images from the European Space Agency, the newest, if you like, generation of satellites. The top picture is nitrogen dioxide. The bottom picture is a lake in Hungary. Earth observation, whether it's by satellite or drone, is really changing what we're able to do. Traditionally, the resolution used to be 10 kilometers, 1 kilometer, 300 meters. Now it's down at 10 meters, and even some of the very small cube satellites, which various organizations are pushing out, you could be talking about spatial resolutions of 1 meter. But along with all of that, we also have the kind of citizen science, if you like, revolution, if you want to say that. What we're carrying around can transform what we're actually able to observe. So these are some of the kind of changing attributes of the data streams that we have, and there may well be others that I'm not aware of. But I want to link back not simply from the PwC environmental challenges, but actually to think about, in a slightly bigger picture, the kind of, I suppose, the push to quantify, to set targets, to have objectives. And I'm going to use the Sustainable Development Goals in a sense to help drive some of this conversation about where statistics and data can help inform. And without further ado, it reflects back to sustainability, not just simply of the discipline of statistics, but sustainability of the planet also. It's probably fair to say, in some respects, everything ultimately is going to be colored by climate action, which is Sustainable Development Goal number 13. These are just a few of the images from some recent IPCC reports. When you think about data here, predominantly it is model-generated data, pretty complex models. There are some observational systems which are improving as well. It's very variable, it's spatially aggregated, it has different temporal resolutions, different uncertainties. But fundamentally, in some respects, how our environment is changing is driven by the climate changes that we're observing. And you just need to look at the BBC every day. There's something else appearing. So, for instance, this morning there's a big article about how Greenland is melting much faster than science had ever actually anticipated. And we're actually even beginning to say, well, if you could measure it to the precision required, sea level as a result of the melt from this summer alone has gone up by 1 millimeter. Now, that doesn't sound like a lot of sea level rise, but if you're living in some of those low coral atolls, that's a lot. Again, this is climate, this is sea surface temperature. Spatial patterns of change are really important here. Now, this is an example where we're talking about, historically, millions of pixels, all with time series. So large volumes of data fused together from different data sources, and that is, again, one of our statistical challenges, how we actually fuse these things together. One of the examples that I'm going to pick up on slightly later is this one about freshwater quality. It relates to the diagram or the figure that I showed you of Lake Balaton in Hungary in terms of water quality. And this is a project which is called Global Lakes that we've been involved in, which is looking at lake water quality across the globe. It's focusing on 1,000 lakes because the technology at the time that this project started meant we could only look at the bigger lakes, but new technology means that we can look at much smaller lakes. So 1,000 will shortly become 10,000. This is an example again, an example again of sensors being put into rivers within England. This is a little bit about a network that we have in a particular catchment in northwest England, looking at the data and how nitrate levels are changing and evolving over space and time. Air quality is another very high-profile topic. And again, we talk about really what's driving air quality, how poor it is in some of our own cities, how we're having to change our infrastructure, how it's affecting health, and how much it costs. So the developments here are small, often less precise sensors that can be placed around a city to monitor air quality, linked to high-resolution models. Soils perhaps don't get the, if you like, headlines they deserve. They're endangered, they're hugely variable at very small spatial scales, and this particular quote just simply reflects the fact that really we need to pay more attention to our soil, because in actual fact, in terms of climate change, it's going to start becoming a source rather than a sink of carbon, which is really quite worrying. Biodiversity, again, very high profile, particularly for iconic species. But again, a recent report evaluating the state of biodiversity globally said that it's declining faster than at any time in human history. And for freshwater biodiversity, land use change has had the largest relative negative impact on nature since 1970. So how do we conserve our biodiversity? Do we care? Urbanization, another sustainable development goal. The landscape that we're living in is absolutely changing. As it says here, nearly a quarter of the world's population live in cities of more than 1 million, and they're just getting bigger and bigger. How can you plan infrastructure, provide services in these types of contexts? It relates also to, there's one or two slight issues here with slide transitions that I thought I had removed, but clearly failed. So apologies for that. This links again to thinking about what's happening within our cities and relating to social inequalities and deprivation. Justice, environmental justice, has been a phrase that's been used for a long time. In a developed context, it's often the poorer bear the major burdens in terms of poorer environmental quality. They're perhaps less well served, and in a global context, equally true. And the reality is, everything is absolutely related to everything. So this was an EPSRC project which we had, which was looking at water, energy, and food. This is just a particular map taken from a very small part of the southwest of England, looking at what did we want to do, how did we need to understand how water, energy, and food in that context was related. Did we have the data to allow us to do it? And the answer was no. So even in our situation of well-developed infrastructure, we couldn't access the data that we actually needed to develop the models to allow us to look at how water, energy, and food in this small system actually interacted with each other to allow us to manage it better. So all of these examples have sampling and monitoring, new technology, new data streams, lots of complexity, lots of uncertainty. Absolutely fertile ground for statistics. And statistical challenges, space-time, lovely, that's what we all can work with. Complex interactions, non-linearities, feedbacks, yep, absolutely, this is just wonderful. Dealing with extremes, non-Gaussian inference, the world isn't really normal, let's forget about that. Computational efficiency, computational challenges related to this. I teach lots and lots of undergraduate students. They probably don't appreciate the many hours, the many days, the weeks that we spend actually working with data before we even begin to model it. Real-time analysis and management, we've got to deliver tools that will help those decision-making processes, help inform them. And part of that is about visualization and animation. And you can tell by the fact that I can't switch the transitions off that I'm not particularly technically good at animation, but there are people that I know who are much better than I am. Now, if you start at the beginning, I've been around for a long time, as Peter knows, traditional training as a statistician, sampling and design of experiments. Goodness, it went through a slump, but absolutely now I think it's coming back and we need it even more. And this particular quote, just basically is an example of an organization that I would suggest doesn't really know what it's talking about, which says, really, you just don't need sampling anymore, forget about it, it's old hat. No, 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 no. I disagree wholeheartedly. And I think of just an example here of citizen science that I mentioned earlier. What we do with our phones, the apps that are being developed, the applications that are being used are really, really exciting. But there are lots of statistical challenges there in terms of the quality, the sampling frame, et cetera, et cetera. And how are we going to link those citizen science data streams with some of our more traditional ones is, again, an interesting challenge. And I've used a couple of examples here from colleagues of mine. This is Lawrence Carvalho's Blooming Algae app. Lawrence is in the Centre for Ecology and Hydrology, and he's developed a telephone app. Sorry, that sounds very old. A phone app, not a telephone app. To look at, effectively, blue-green algae when they occur in lakes, so that individuals who are out walking their dogs or just going for a nice walk in the countryside can actually pick up a photograph, send it in, and it will come back and say, don't let your dog swim here, please, et cetera, et cetera. This is an example taken from the literature about social media using Twitter to look at air quality in Beijing. The two diagrams basically include the Twitter feed, if you like, inferences drawn about air quality, along with some of the more traditional sensor detection of air quality. And they look pretty good. So the question then is, well, do we need these automatic, expensive sensor networks? But do we actually benefit from having multiple sources to inform us about the air quality in this particular city or any other city? Oops. Environmental hazards. Oh. I have a colleague in Italy who has developed a very simple app on mobile phones, it's all for Android phones at the minute, to detect earthquakes. Now, this is a situation where you could say, well, lots and lots and lots and lots and lots of people have these. You just need to have it plugged in online. It will send triggers to the server to allow, if you like, early warning of potential earthquakes. This is in competition with very, very expensive geological, if you like, monitoring networks for earthquakes. So again, thinking about how we combine that information together, or indeed in the picture on the right, how we move around cities, et cetera, et cetera. So sampling models. So George Box, wonderful, all models are wrong, some of them are useful. But then again, we get some quotes like this that, if you don't even have to settle for wrong models, you just don't need models. No, 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 no. This is, again, an argument that we need to, if you like, counter. Absolutely, we do need models. Models help us explain, they help us understand, they help us predict, and so on. Visualization, pictures and words. Now, this quote I absolutely can agree with. The other two I don't like. But in that sense, data visualization is key to actionable insights. So it's not just data, it's model visualization is also key to actionable insights. So really, that's part of this narrative that we need to become, I guess, better at producing. So lots of challenges here in terms of structured and unstructured data, temporal and spatial, but often different granularities in both space and time. Sparse, but still sparse in the context of lots of data. Missingness, but not necessarily missing at random, and absolutely very noisy. And these two examples, the picture on the two panels on the bottom are again lake water quality from a remote sensing project that we have. And the set of charts on the right are just basically a little sensor sitting in a small stream in a rather rural catchment in Scotland, recording water attributes every 15 minutes. And you can immediately see some of the issues about, as I said, variability, gaps in data, how you begin to think about modeling this. Now, 15 minutes is hardly high frequency. If you go down to 4 seconds, which is quite routine in many other applications, then again, we have to think about what the signals are in the noise that we see. So what I'm going to do in the second half, which I think is about the right time that we have, is just pick up on 2 particular examples to give you a little more information about some of the statistical methods that we've been using. So I mentioned Global Lakes. This was a NERC-funded consortium project to basically look at, as I said, lake water quality over time and over space using satellite imagery, in situ measurements, and so on. And like all true projects, as soon as we submitted the proposal, the satellite whose data we were relying on for a more kind of current picture of water quality went offline. So that's why, in some senses, the timeline was a little disappointing, and there is a gap. And now we're basically, if you like, rolling the same type of approach out to the newer satellites that we have available. Now here what we were looking at particularly were various water quality parameters, temperature being one, which of course is a lovely, lovely, lovely variable, and chlorophyll, which is a less lovely variable, as you'll see. And we were effectively tasked as the statisticians in the team to find ways of generating meaningful ecological clusters of lakes. So we were looking at identifying temporal coherence across these 1,000 lakes using a large database of satellite imagery. So each lake, you would have an image approximately 2 weekly to fortnightly, and over effectively, I think it was ultimately ended up being a 12-year period. So these are just a few of the kind of pictures that you can imagine. The blue and green picture on your right is just actually what the data might look like for a particular lake. The map of the world just shows you where the lakes are located, and the panel in the middle just shows you one of the time series for a particular lake. So our statistical solutions to these problems were to use a functional data approach. So we've used functional clustering to effectively produce the clusters of our lakes. We've used pattern identification using a state space functional principal components analysis to look at the spatial images. And we've developed a statistical downscaling approach to fuse together the satellite and the in situ observations. Now, this is an example of the older technology. This is Lake Titicaca. This is lake temperature, effectively monthly data, resolution probably 1 kilometer. The fact that nothing's happening at the minute is just basically telling you there are large periods of time where you have no data, you have periods of time where you have limited data, and then you have periods of time where you're fairly well covered. And it's not predictable in the sense of absolutely, but you can imagine circumstances when the gaps occur. The panel on the left-hand side is actually the retrieval error which is produced by the satellite specialists. So we have an understanding a little bit of some of the uncertainties in the measurements. This is the next kind of generation. This is chlorophyll, which is the other variable. This is more or higher resolution. This is Lake Pepsi. There's something like 70,000 plus pixels here compared to the kind of 6,000 or so in the previous panel, again reflecting just how things are evolving. And again, you can see the missingness, the sparseness, and in some senses with chlorophyll, the much, if you like, more varied patterns that we observe. Newer satellites, the Sentinel series, you're talking about 10-meter resolution. The CubeSats, as I've said, you're getting down to potentially 1-meter resolution. So it's changing how things are basically being recorded in a very big way. Now, the functional data approach you can apply to the time series at pixel level for a lake. You can apply to a lake mean curve in that sense. So you can either have 1,000 mean curves, or you can have, for each of those 1,000 lakes, 70,000 time series, or in the case of the really big lakes like Erie and Superior and so on, you're talking about millions of time series. Now, the kind of basic idea here is just simply we produce a smooth curve for each of those time series, and we effectively use that as I suppose, a dimension reduction approach, because we focus in on what the coefficients are in terms of the spline coefficients in the smooth curve fitting. And that's really the essence of it. So as I said, take a pixel or take a lake, produce the time series, effectively smooth that time series, and then we can begin to extract the seasonal patterns and the long-term trends, and then we can start clustering those. So this is a picture from a recently submitted paper, which is actually summarizing all of the work that we've done for lake surface temperature. The data for the lake surface temperature is all publicly available. The chlorophyll data, not yet so, but will be coming along. Again, we've used lake mean curves, we've used k-mean clustering to effectively identify the seasonal patterns in these different curves, these different lakes, and effectively map that into space to see whether or not we can see any sort of consistent patterns in that sense. And the ecologists seem to love this. They're now talking about, if you like, defining, well, ecoregions except in a kind of a lake sense, in that sense, and beginning to think about what the drivers of some of these clusters actually are. Fusing different data sources is really important in this context. You know, in situ data tends to be expensive. You get out in a boat, you get your feet wet. In my case, you don't like it very much because it can be slightly rough. It's generally regarded as being highly accurate in that sense, but it's costly. And there usually tends to be a very small number of locations that we have this in comparison to the remotely sensed data where you've got a lot more information. So you've got to try and find ways of bringing those together. And again, just a little example from a work of our postdoc, Craig Wilkie, published just this year in Environmetrics, looking at this downscaling approach of fusing together, in this case, 9 in situ locations in Lake Balaton in Hungary with the satellite data, which correspond to just over 7,500 pixels. So picture on the left shows the satellite image for a particular month with dots, the black dots that you might just about be able to see representing the sampling locations. If your eyesight's really good, you might be able to see that the color inside the dots doesn't seem to be the color that's surrounding it, so that's just reflecting the differences between the in situ and the satellite. The middle panel just shows you for, again, a particular pixel, the different data sources that we have, and then the rightmost picture just shows you the smooth curve that has been fitted and how it ties up with the actual observations that we have. Again, the approach here is to fit smooth curves, both to the satellite data and to the in situ data, to extract the coefficients and to build a regression model linking the coefficients between the in situ and satellite data, which then allow us to make, if you like, improved predictions of what the actual concentration, either temperature or chlorophyll, is at any location where we don't have in situ data. So again, a few equations just to kind of prove that occasionally I can write down an equation or two in that sense. But as I said, Craig has done all of this, so that's really good in that sense. But it gives us, again, a way of propagating again through thinking about the uncertainties and representing what's happening in our lake. And again, these just simply show the map of the lake on the top shows effectively the end product of this data fusion. And now the circles and the colors in the circles are much more consistent with the colors around them, as you would anticipate, because that information has been included. And we've also got standard errors for the predictions across the lake. The last example is an ongoing one called Hydra Scape, which again is funded by NERC. This is about modeling landscape connectivity and biodiversity. There's a number of partners, and again, we are the statistical group who are effectively been tasked with finding models that link biodiversity data that we have around lots and lots and lots of potential explanatory covariates, which our ecologist colleagues keep talking about connectivity, but they just mean explanatory variables. So that's good. It took us a while to understand that, and that's part of the challenge about collaborations, is just becoming familiar and comfortable with the language that each of our disciplines tends to use. So here we're bringing together data from lots of different sources, including national recording schemes, citizen science, and, if you like, regulatory monitoring schemes as well. So we've got lots of different species. We've got macrophyte, odonata, birds, fish, beetles, mollusks, etc., etc. We've got different types of response variables. We're using richness and abundance. We've got the spatial scales of observation, 1 kilometre grid cells, water bodies. That's the kind of choice that we have. The types of connectivity or explanatory variables that we have, we've got hydrological explanatory variables. We've got landscape variables. We've got riparian variables, which relate to what's happening around the water body or lake edge. And we've got some environmental stressors, including land use. And this reflects, again, the driver, as I've said, in that 2019 report that talks about how land use change is one of the most detrimental drivers of, if you like, biodiversity change. We've been building a two-stage modelling approach. For those of you that you've got a chance, there's a poster out, number 4B, which is one of our PhD students who's been working on this, has a poster describing particularly the stage 1 modelling. We've got a huge, well, not thousands, but hundreds of potentially highly correlated environmental variables as explanatory variables. So there's a little bit of thought here about how we choose those, and then once we've made that choice, how we then build the model to link the connectivity and stressors to the biodiversity. We've been using random forest to help with this variable selection, but having been at a session earlier this morning, I think I'm going back to rethink that, and maybe I'll be trying to persuade our ecological colleagues that we don't just want one model, we need multiple models. So I'll be in touch with Heather. Ecologically, we've had a lot of toing and froing and a lot of discussion about what is perceived to be important ecologically. And as we've said before, statistics is part of the support mechanism. It's not going to be the only argument that's going to be, if you like, driving forward the decisions that are made. So we've had to think about, as I said, variable selection, addressing high correlations, thinking about transformations, or as one of our master's students who's doing a data analytics program described it, feature engineering. So in future, I'm not going to talk about log transformations. I'm going to say I have feature engineered this particular variable. And it sounds so much more. And then we've used GAMs, so again, smooth regression models, including bivariate terms, to help us begin to develop the ability to explain and visualize what might be changing in their biodiversity and how it's being driven by some of these explanatory variables. Now, as I've said, it's been quite a challenge. It's taken us quite a long time. This has been a 4-year project. We're now in 4 years, in the 4th year. Probably the first 2.5 years were devoted to actually pulling together the data, getting it into a format that we could actually work with, figuring out what the spatial scales were that made sense. So you cannot absolutely underestimate the time that it takes to become confident about the quality of the data that you're working with. In this context, the interactions between the connectivity and the stressors are going to be key. And this is going to be a situation where we don't expect there to be nice linear relationships. We do expect there to be some feedbacks, and we do expect there may be instances where, in fact, the system that we're looking at may flip from one state to another, relating back to the kind of resilience argument. So, are we sinking or swimming? I'm almost finished. Sampling and monitoring, yay. But we have to be much more, if you like, proactive in pushing the ideas that sampling isn't completely out the window and we don't need to think about it anymore. We need to be, I think, alert to some of the data quality challenges in terms of dealing with near real-time, near, high temporal frequency, high spatial frequency, and so on. So the data world really is changing. And we need smarter, better, faster, if you like, statistical tools that we can then get out there to make a difference in terms of thinking how people are talking about what the environment is actually doing. So this slide just actually repeats what I've said before, but it's also saying that we still need this. Those are the challenges that we're being confronted with in the context of this changing data environment or landscape. But I'm very optimistic that as a community, we are very much moving forward and delivering, I think, real-world, impactful, useful tools to assist in the decisions that need to be made, and perhaps need to be made pretty rapidly. So as I think it was Charlotte Watts said in her keynote, you know, it's not sometimes the case that we can afford to be a bit complacent and say, well, give me 3 years funding for a PhD student and I'll give you an answer at the end of it. Sometimes we're going to have to be much quicker than that. So we're here. We're useful, absolutely. So this particular final slide is just saying, I think, what some of the remaining challenges are and why we should care. 50 years since man landed in the moon. I'm hoping that I'm okay to show this image. I did kind of try desperately to find a kind of copyright-free one because I wanted to end on that. We have a responsibility to a very special place. We've nowhere else to go. We're not going to move to Mars in the near future. So as statisticians, as concerned scientists, as concerned citizens, as people with children and grandchildren and so on, you know, we have to step up. We have to get engaged in this conversation. And as I said, there's lots of big questions still from the kind of methodological point of view. So please, all of you early career people, this is a hugely rewarding area, hugely fascinating problems, and it's making a difference, I hope. So there we are, and there's just a few references there. So thank you very much.
Thank you, Marian. The floor is open for questions or comments. I have many, but I am certainly only going to ask them if nobody else from the floor starts asking questions real soon now. Well, I'll kick off with one. And in fact, it's not there, but you actually had a phrase, sparse data. And I wonder if a better term is sparse information, because I have a very strong suspicion that in a rather general sense, the correlation between the size of a data set and its information content is weaker than a lot of people assume.
I think that's a very good comment, and absolutely, I think that would be a very fair comment to make, because as I said, the reality is that often, you know, we're confronted with these very large data streams, and their immediate reaction is actually some form of aggregation, whether over time or over space. I think the challenge is figuring out what the correct aggregation would be to address the environmental problem, and that's where I think that information is a very good way of describing it.
Yeah, in fact, it's probably 30 years since Stefan Lauritsen, whom some of you will know, said to me that one day we're going to need a theory of how to throw away data efficiently, and yes, that's, I think, what you're talking about. Yeah.
Yep.
I could go on all day and keep you from your coffee, but thank you.
Thank you. Jane Hutton, University of Warwick. Actually, when you talked about sparse data and sparse information, it brings to mind Charlie Meng's talk in Manchester. We talked about how much information you need to get an unbiased estimate. I think that's critical in trying to communicate to people that, I think his example is, you know, a simple random sample of 100 is more efficient than you've got to go up to something like 60 million from big data to get the equivalent.
Again, as a comment, I absolutely agree. I think that's really, in some senses, reflects my perhaps slightly tongue-in-cheek comment about, you know, you don't need to sample anymore. I think the benefits of statistically based sampling and design, where it is possible, clearly in some environmental contexts it's not, is actually immensely valuable. And I think we've slightly, well, when I say we, I'm not sure the statistical community have, but I think it has been slightly lost sight of in some of the slightly over-egged comments about what very large big data might actually be able to do.
Hi, you had on the picture of the lake in Hungary, I think, where the colours that you got from the satellite and the colour from somebody on a boat were different. Does that worry you at all, that there's the difference, and how do you try to characterise that uncertainty between the measurements?
No, it doesn't worry me. I think it reflects the fact that they're, in some senses, while they are both trying to give you knowledge or information about the same physical quantity within the lake, they have very different, if you like, measurement properties in that regard. So the reality is that what we were trying to do was to say, we're not saying one is right and the other is wrong. We're actually saying both of them are informing us about what's happening in the lake and what this particular measurement actually is. So let's use that information together to give us an improved map of the concentrations in the lake and effectively an uncertainty on what that value actually is. If you speak to the satellite people, or if you speak to the chemists who are doing the in situ monitoring, there's always a little bit of friction potentially about who's right and, et cetera, et cetera. But as I said, the idea here is just simply we're trying to say both of them have qualities which are useful to allow us to produce an improved map of lake concentrations or lake surface temperatures.
I just wanted to ask, of course, you presented a whole arsenal of methods, including the method that we heard on the last section with multiple models. But when using different data sets, in the last example, it is possible, interesting to point also to the work on data linkage, which is developing in few last words, possibly Genevera Allen and so on. It might also be relevant to this last topic.
Yeah, I mean, in that sense, it's absolutely about data linkage. We don't have the same issue around, as you would have in public health, about potential privacy issues and so on. But we do have, in some senses, this is an easier data linkage problem than you would typically have, simply because they are being linked through their spatial coordinates. And pretty much, we're reasonably confident that we have those known with very little uncertainty, particularly through GPS. But the challenge is that the geographical coordinate, for instance, for the satellite data point might be a grid cell, which could be 10 meters or could be 1 kilometer. The geographical coordinate for the in situ is a point. So that's, if you like, the nature of the linkage, but it is actually, as you say quite correctly, it is just about data linkage.
I'm just wondering, is there any evidence you have about how this use of big data is kind of moving into schools and education, or are kids still just throwing little squares out and writing numbers in their notebooks?
I'm not familiar with quite what's happening in schools and education, but I can definitely tell you about how it's being rolled out into environment agencies, for instance, who are very much looking to these types of data to, in some senses, allow them to scale back perhaps some of the more time-intensive, cost-intensive routine sampling that they do. So, for instance, the Scottish Environment Protection Agency are working with colleagues in Stirling, who are part of Global Lakes and Hydra Scape, to look at how Sentinel data can allow them to effectively report on the Water Framework Directive requirements for particularly very remote and quite hard to get to water bodies. In that sense, the European Space Agency and so on, I think, have a very big educational campaign, but I'm not quite sure how far it has, if you like, percolated down. I know they're certainly working very hard with lots of universities across Europe, but whether it's quite got into schools, I don't know.
Thank you. It's a really interesting talk. I'm just reflecting on the range of methodologies that have been used from sort of very big scale data, which have various quality implications to sampling and models, which of course have different quality expectations. And I just wondered, within your research group and within your discipline now, are you thinking about quality and therefore the value that the analysis will add to the sector? Or is it all very experimental still because the pace of data and the pace of change is so fast?
So both Global Lakes and Hydra Scape, which are the two more recent ones where there's been a lot of use of data and are driven by, obviously, research questions because they're Research Council funded, but we have a really quite strong relationship with a stakeholder advisory board. So in that sense, we have meetings, stroke teleconferences with them, not every month because they're very busy, but probably every 6 months, where we present and we talk to them about how what we are doing might be used in their business context. The river network work was done specifically with the Environment Agency, and we're continuing to work with them as they are evolving how they redesign their monitoring network. And one of the things that they particularly wanted to have, my PhD student and colleagues, we developed a couple of our Shiny apps so that they could actually visualize their own data and look at, if you like, some, I suppose, scenarios of what would happen, how would things change if we did this rather than that.
I'm going to abuse my position as chair once more very briefly to say you touched on language and having to understand that feature engineering is just transforming lives. The one I think is particularly insidious is the use of the word data to describe nothing of the sort, but the output from a model. And the reason it's insidious is because a statistician who isn't directly embedded in the research group that generated that image tends to believe its data and treat it accordingly. And I think that's a real concern for the validity of the inferences that are drawn. This is going to have to be the last comment from the floor, I'm afraid.
Thanks very much for such an interesting presentation. I have a question about something that you raised at the beginning relating to curiosity underpinning the work of researchers and statisticians. Certainly within the field of social sciences and criminology, it tends to be the case that our work is about solving problems relating to policy. And I'm just wondering if you find that that actually curbs some of the creativity and innovation that we could be doing within the field of academia.
Speaking personally, I guess my view has always been I would like what I'm involved in, what we're developing, to help in informing policy decisions. I'm not sure how much it does make a difference in some senses because, as I alluded, I think it's only one strand in terms of how a decision is made at a particular level. I think that as well with the kind of growing push around digital environments, the fact that the government has set up an Office of Artificial Intelligence, and that there's a lot of discussion about open data and open data initiatives at government levels and so on. I think it does mean that the doors are kind of opening wider now, and there are still a lot of hurdles. I think, being innovative in terms of approaches that we take are going to be really important. And I think it's back to that narrative and that communication, which is where if you like, the pictures, the ability to interact with those pictures really matter. I think someone said yesterday in the kind of panel discussion, it is, although I find it very difficult because he made a comment that said, don't tell me a story that's every line is caveated out about some uncertainty, or I'm only 92% sure about this, etc., etc. That's the language that we use. And in some ways, I'm probably saying, well, actually, we need to move some way towards the other communities, but they probably need to come a little bit towards us as well to reflect the fact that uncertainty is just, bread and butter, and we need to kind of acknowledge it. And that's where I think that the pictures, the modelling really help. Are we top priority in any of the kind of engagements that we've had? Probably not. Are the agencies interested in what we're doing? Yes, but only as it immediately addresses what some of their day-to-day or slightly medium-term challenges actually are. Very few organisations these days seem to have enough bandwidth to take that longer view. It's often, you know, we have to solve this problem now, or this is coming along the lines, or what's going to happen in the UK once we leave Europe, and who's going to manage all the environmental regulations, what are they going to be, who we're going to be reporting to, how we're going to be reporting. Those are some of the really big, if you like, problems that are confronting many individuals in DEFRA, the environment agencies and so on right now.
Okay, we are going to have to leave it there. I think it's very clear from the discussion that Marian's given us a very thought-provoking lecture. And before I hand over to Lucy Tees for the 10th birthday celebrations of YSS, please join me in thanking her once more. Yeah.
Thank you.